Okay. Good. Okay, so as promised, this is going to be the most math-heavy class, most math-heavy lecture here. After that, it'll get easier. Also, next week, Josh will go. So those of you who are scared right now and are just watching that online, you can the class. Josh will some more practical techniques for instance, selecting models. But I think it's important to understand and why some things actually do work. So we're going through a few papers, some of which are quite fundamental in the sense that before that there wasn't really much analysis in terms of what is overfitting bad for you, what guarantees can we get, and so on. Okay. So what we had as a starting point last time was basically kind of found, and in it we got basically something from a single test, but then was L, which was like who is uncomfortable with that? Who has questions about how we got this? This was basically invoking a single test, basically, this is like a single function error, and then saying, well, okay, if my training error is like 0.3, then 0.3 plus this number is going to be probability, namely minus delta, an upper bound on my test error. Okay. Who has questions? How about how we got there? Yep. So L is basically an loss. So for classification, you can't do worse than getting it wrong. So L is for regression. There's a socket in the wall. Then, well, there's an upper bound on the voltage that you could see there, because otherwise, all the insulation will shorten out. So L might be 1,000 volts. Right? Maybe, well, let's hope that the insulation is a little bit better than 1,000. But basically, there are reasonable upper limits that you can impose on what you expect to see. And the tighter you can make those, the better it is for you. Or for instance, if you are in computational advertising and the existing system, maybe was doing sort of okay and you had a 1% click-through rate, then even if you get a genius statistician in and he will do some miracle system, it's quite unlikely he'll boost that click-through rate to more than 10%. As in, if it's more than 10%, it probably means that something's wrong with it. So bound rate, very problem. Bound for which you don't need this guarantee and you only need the first and the second order moment to exist. Excited you're about it, you might actually get some of this in the assignment. Maybe as an extra credit. So that. So now suppose functions, wrong with only probability 1 minus, well, delta over n, right? Because if we can go wrong with only delta over n probability for each of them, then the sum over all those terms, of course, can only got this inequality that's basically here, namely that epsilon by working out that n is the size of f, and then it's really just simple algebra exactly the. And this means that you get the following statement with the probability that the sup over all functions f in this function class of the empirical average, so 1 over m sum over I going from 1 m some loss function of, you know, xi, yi, f of xi minus the expected value of this loss of x, y, and f, right? Here is greater than epsilon. This thing here is less equal than delta. So that's why it's a uniform convergence bound, because it basically means that uniformly for all the functions in this function class, you get this convergence. So you get this for both the really good, you get it also for the functions that are quite useless. Okay. Now, does somebody have an idea how you can improve this? Okay, so remember what I just said. This guarantee works really well for both the good functions and the not so good functions. Oh, yes. Yeah. Sorry about that. Audience medium. Yep. Okay. Thanks. Yeah. Okay. So. Okay. So, does somebody have an idea how you can make this better? So, I mean, do we need this guarantee for the useless functions, basically? Well, we sort of kind of need some guarantee for the useless functions, but it doesn't have to be quite as good. So, suppose, you know, these are the losses for the various functions, right? Maybe I have some here, maybe this one does really well, and then some others that don't do quite so well. So, obviously, have rather coarse guarantees, that's fine, right? In other words, if we just knew the function was good, we could actually distribute our accuracy and our penalty accordingly, right? So in other words, I don't really need to know really well all things that don't really work anyway. That's reasonably straightforward, is to make a bet beforehand. So the bet beforehand basically means I'm going to go and say, well, actually, I think those functions and these functions and distribute formally over all the terms. I give which I think are likely to do it well a larger fraction of the full delta, and I give those which are quite unreasonable a very tiny fraction of the delta. Through this, get away with, in this case, basically an infinite function. You know, I will just give them smaller and smaller fractions, and as long as it sums up all to 1, everything is good. So what now happens is that this uniform here would acquire a term that depends on which function I'm looking at. So in other words, my epsilon might very well depend on whether I pick a particularly extravagant function, whether I pick something that I consider very typical. So this is sort of the way to, for instance, pack Bayesian bounds and so on. This is also how you do structured risk minimization, because usually nobody tells you exactly which function contains everything. This is way beyond the 10701, but it's a very important concept at least to think about. The other thing that this does is it tells you, for instance, for an active learning algorithm, I could, for instance, a small set of data. I get course bounds. I figure out, well, these guys are not useful, and let me then just squeeze in the neighborhood of where I observed it. You basically iteratively refine and keep on discarding things where you don't really care. This also is something that you want to use, for instance, in the context of bandit algorithms. So we'll eventually get to bandit algorithms in this class. So, but just as a quick insert, a time when people didn't use us for armed bandits in Las Vegas yet, there was a little between the just because they're mechanically different devices. And of course, your goal is to lose as little money as possible, possibly even win some. And you have maybe 100 bandits in front. You need to figure out which one. And then you can start thinking about where you iteratively refine the confidence for each of these terms. And then you pick the bandit that actually still being looking at rewards. You're basically looking at the current estimate of the reward plus the upper bound of how uncertain you are, to make sure you don't over fashion, but actually browse today and you've seen ads exactly how people determine which ads to show. These are effectively running somewhere behind the scenes. Or for instance, if you go to LinkedIn and you look at their news feed, they basically run a bandit algorithm. So with that as an insert, have a discrete function class. And let's say if I have binary loss, well, maybe I can't really do things very efficiently there. Maybe there are other clever efficiencies that I can exploit for binary loss because, well, I can, I only have two possible outcomes. So therefore, I can get equivalence classes. Okay. But is the basic principle sort of kind of clear at this point? Everybody's very quiet. It's not a good sign. Okay, let's say we have a function class that looks like so. Okay, and there are lots of functions in there. So then, if I perform the soup over all functions as function class and I have to count them, then obviously the log of bound becomes useless. So what can I do? So what I can do is I basically go and approximate this function and I cover. So for instance, I pick some balls of some size epsilon, and then I count how many balls I need. Let's say epsilon is 0.2, and I have, well, 7 of those balls. And so now my guarantee will be 1 on the number of, and also on the I don't know. Okay, so why are we guarantee that works for all the functions in the function class? Because before I invoke the learning algorithm, I don't know yet which one is good. So you need to make sure that the choices that you could make, all of them are well behaved. Function here is really good to get the guarantees for that, but since you don't know yet which one's good, it's kind of hard. So this is exactly why the uniform mentioned before is having the same equally stringent criteria imposed on all the functions in this class. So for instance, there is a paper by Compositions where he decomposes his function class into functions that perform really horribly, somewhat mediocre, good, and really amazingly well, and then he stratifies the bounds accordingly. And if you do this clever for slightly better guarantees, this is way beyond 10701.
Maybe another way to answer the same question. Our learning algorithm is trying to find the thing that has lowest error, let's say, right? And so if we want to know how much error does the thing we find actually have, well, there's two things that are happening, right? There's the error in estimating how good each one of the functions is, and then the algorithm, then there's the error that each one of the functions actually has, right? And so, we're probably not going to pick a function that's actually really, really bad because, the data tells us that that function is bad. But out of the, 100 functions that are all really good, well, we'll probably pick one that just got lucky, right? That the data makes it seem better than it actually is, right? And so what we're trying to do is say, okay, for each one of the functions, we're using the data to estimate how good it actually is, right? And if we put a uniform bound on for all functions, we don't have more than this much error, then for the best function, we also don't have much error, right? So it's basically a way to put a bound on how lucky the best function got.
Yeah. So all we are concerned about for this class is uniform bound. So non-uniform bounds are really beyond the scope of this class. Well, they actually sort of kind of will come back in the context of Bayesian method. So in the context of a Bayesian method, you are going to place a non-uniform bet over the solutions that you're going to see. But for the purpose of this frequentist analysis here, we'll basically make a uniform assumption. Okay. So if you think about it, if we discretize things by, let's say, epsilon, then well, I'm only using these as reference functions, plus then square root basically the size of f muted it at scale epsilon plus log of 2 over delta divided by 2n. And here we have our. So this is essentially the result that we get from this. So we now need to, and this is assuming that, the loss is actually Lipschitz in this epsilon and so on, and I've already picked my coefficients in the right way. Otherwise, so for instance, if I change my function only by 0.1, then here I'm assuming that my loss also only changes by 0.1. Otherwise, you need to multiply this epsilon by an appropriate number. Note that this is only looking at the guarantees. It doesn't actually affect the algorithm. In other words, I may very well pick, the best out of an infinite class of functions, for instance, by convex optimization. I don't really need to know any specific discretization. I just need to know that if I was to discretize things at a scale epsilon, then I would have that many balls. So for instance, if I pick more balls, then you can see that the error is going to be smaller, but the number of balls is larger. And so the entire game is now to say, well, actually let's look at the inequality here. So this is called the covering number of a set. That if I make epsilon small, this number blows up, and this number goes down. If I make epsilon really large, this blows up, and this will go to 1 at some point. And you want to basically find the epsilon for which too large. Now you can this choice of epsilon will depend on m. So what you're effectively doing is you're saying, well, if I have a lot of data, I can look at my function class with a very fine level of discretization. Whereas if I have a very tiny sample size, so if m is tiny, then I better only pick something for which log n is small. Okay. Well, n is the number of balls, correct. That's why it's called the covering number. Actually, I cheated a little bit because what you need in order to make this well defined is you need to define what I mean by a ball. Because balls aren't necessarily L1 balls, right? I mean, okay, balls aren't just that, but this can be a ball. Or this can be a ball, right? Ellipsoids. Or this could be a ball. These are all balls with regard to some metric. So reset, what do you think about, how balls are defined? So now, okay, let's see how to best explain. Okay. Yeah, I think that's pretty much all that you want to know about covering numbers. Yep. So L prime was exactly this Lipschitz constant that I swept under the rug before my notes. And that's basically just, if I change my function by epsilon, then how much does my loss change? And of course, I have to assume some degree of continuity in my loss function. So for instance, L1 loss, L2 losses would do the trick. Binary classification losses actually don't. So what sometimes people do, if they have to get guaranteed binary classification losses, they say, well, let's upper bound the true loss, which is maybe this here. So here the loss is, here it's 1, and here it's 0. And here it's basically, we're looking at y times f of x. And you upper bound this by some convex function. Right. And if you do this, you can see that, get a there, you then pay yet another price, namely you're actually to get your bound in terms of some surrogate loss function, which isn't really what you want to do. And so you have basically this entire chain of arguments, right? So you first have the empirical loss with regard to this. Then you say, well, this is well concentrated. Basically one further inequality here on the left. Because all the statement here would be with regard to the wrong loss, and you know that this upper bounds the true loss, so everything is good. Minority bounds are usually pretty loose, which is why you want to use them to understand the scaling behavior. Like, for instance, the 1 over square root sample size, that is actually tight under reasonably general conditions. The constants are completely hopeless in general. Also because bounding this number here, well, okay, I'm bounding those numbers. And it's a lot of math you enjoy if you like Banach spaces, and then you don't do otherwise. And I think we did a good job, but it still wasn't good enough. So basically, making those bounds useful in practice is non-trivial. But it's good for qualitative arguments to understand how things will change as stuff changes. Okay. So just a little bit of about how those bounds affect things. Let's look at d-dimensional space. Take simple cubes. And of course, if I have my original matrix this covering number here, is going like what? I have a unit cube, and I try covering it all the unit cubes. What does the function look like? Epsilon to the minus d. Epsilon to the minus d. And I'm just making this order because we have all those quantization effects on the corners that I'm not going to worry about here. So, what this means is that basically this is exponential in the dimensionality of my function class. This is why also sometimes people talk about the curse of dimensionality. Because now if d is really, really large, let's say you're using a linear classifier with maybe 1,000 parameters, which doesn't sound like such a great deal, then you basically have epsilon to the minus 1,000 as the growth parameter here. Fortunately, we have the log will be reasonably behaved. But what you now get is your d log epsilon. The entire equation will be something of the form d log epsilon divided by m. It will be that order. So this is why it's not such a terrible idea to look at the ratio between half. That's why I told you, well, this is a way of looking at scaling properties, at looking at qualitative properties. You get meaningful results fairly quickly there, but not necessarily explicit constants. For instance, this gets a lot more hairy if I tell you, well, okay, you've got the unit cube, but I let you cover it with balls in an L2 sense. And you can write papers about just that thing. Okay. Any questions so far? So now for something seemingly totally different, but it's actually quite related. And I'll just quickly mention it to you because it's important that we all know what it is, but I wouldn't recommend you to use it for any practical guarantees anymore. It's called the VC dimension, named after Vapnik and Chervonenkis. So they wrote absolutely groundbreaking papers, some of the most papers in our area. First one in 1971, then another one in 1981, and then a few other ones which were maybe still quite relevant but not quite as groundbreaking, but those first two papers were stunning. Okay, so what did those papers do is they basically essentially proposed and started that entire reasoning that I've been explaining so far, namely that you can actually get guarantees for large function classes, imposing uniform convergence guarantees by measuring how complicated or different various functions are by actually doing all this thing. And the quantity that I hit upon is what's called the Vapnik-Chervonenkis dimension in the honor. And you may sometimes see this as the Sachs-Elach lemma, which is, so there's a long story about why 3 papers on essentially with information getting out of Soviet Russia, not quite as it should have, and some people already having some preview information, and apparently one of the missing puzzle pieces is that Erdős gave one of either Sau or Schelach the result as a problem. The guy solved it and published a paper. And it basically sounds like a story of, you know, not very well controlled information release. Okay, anyway, you would call it they got scooped. But anyway, they published it at the same time. It's just that this stuff wasn't well known. So what is the Wapnick-Javoninkas dimension? It is a measure for binary classification. So this is all classification. So it's a little bit more restrictive than what we have. It's also a lot earlier than, in a way, the more modern argument that I was putting through now. So binary classifier, so it can output 0, 1, or let's say 1 and minus 1. And I'm going to ask how many points can I classify with arbitrary labels by using this argument. So for instance, if I have a linear classifier, you can obviously see that you can separate, you know, pluses from minuses in arbitrary ways. But if I have 4 points, it's not possible to separate them in an arbitrary way anymore. So what happens is basically there is a regime up to which the number of possible dichotomies for that set grow exponentially. And the VC lemma, or Sauer-Shelach lemma, then states that at some point this switches over to a polynomial growth with a certain exponent. So this is a fairly general result about what you have for function classes that can generate binary outputs and how you can actually then turn this into, you know, measures of how large these classes are. This also has to do with what's called falsifiability of scientific theories. So you may or may not have heard of that, but basically the point is if I come up with a scientific theory, let's say how the world works, let's say, you know, how protons or whatever interact. And if my theory cannot be falsified, in other words, if I cannot design an experiment which can clearly refute my theory, then this is not a valid theory. So that's why palm reading is really a valid theory of how people will behave, because the palm reader can always say, yeah, but you know, something went wrong, and by the way, the moon changed, or maybe you scratched your hand. So if there's a limit to how many excuses you can come up with, this is a valid. And in the same way, if there's a limit to how many ways how you arbitrate function class, at some point you can state with some confidence that the solution that you've picked is right. Because effectively what you're doing is you're coming up with a theory of how positive and negative labels should be assigned. If your function class, you know, has, you know, a function for any arbitrary assignment, then how do you know that you ended up picking the right one? You don't. Okay. So with that aside, let me just very, very briefly show you what the theorem is. Basically it goes as follows, that the risk is bounded by, you know, the empirical risk minimizer, basically the best thing that I could have done on my training set given my function class, plus a quantity that should now look very familiar. So we have our log delta, we have our sample size here, and then here we have an h of 2m over h. Okay, so h is the VC. We tell we have polynomial growth beyond h. So what you also see is that you really want to have a sample size that's larger than the VC dimension. In some cases, the number of parameters are the same thing. So for instance, for linear functions, it's straightforward, right? So basically, you know, linear functions in the dimension are straightforward. Nonlinear functions where I have a linear combination of them that are linearly independent, it's also plus 1 coefficients. So this is an affine function, right? That's why. So very, very good remark. In fact, this is something that pestered people for a while when they tried to do VC analysis of SVMs because they had a constant offset. you need to be careful about those things in this reasoning. And yeah, excellent remark. So what you also see is that, you know, this is a similar behavior. So the epsilon is essentially this quantity. That's how closely you look at your function class. And you actually only need to look at it as closely as, you know, 1/2, because you only have outputs of 1 and -1, so nothing else really matters. And so you get this exactly the same type of behavior. As specific coefficients, I don't think you need to remember them in any way. The only thing is to remember there is that this is a reasonably straightforward way of measuring how complicated the functions are. Here's a cute example. The function sine x over w has infinite VC dimension. Sorry, w over x. I apologize. This is a typo. So here's why. Okay, I haven't really drawn it very well, but basically the frequency decays. Now, if I have arbitrary labeled points, let's say I have some points here and some points there. Okay, well, maybe that's wrong, but okay, I guess you get the point. Then I can just be clever about choosing this frequency. You always squeeze positives into, you know, the positive branch of this function and the negatives on the negative, because I can essentially in arbitrary ways space things. At least there exist points for which I can do this. I can't do it in general, but I can points for which this happens. And this is why the VC dimension then is infinity. Okay. So that's all I really want to say about the VC dimension. Again, take a statistical learning theory class if you want to know more about this. Any questions so far? Okay, so what I can do is, see, the frequency here becomes infinity because the function is w over x. So this will wiggle like crazy up here. So actually the limit for series is not even well defined. So therefore, by just choosing w suitably, I can always get, you know, a positive or a negative lobe for any position that I want. This is essentially how actually have to exploit the entire dynamic range of real numbers. So floating point numbers on a computer would fail, right? But if I use real numbers, specify things at arbitrary position, wrong. There was a question up there.
Previously, we were looking for the maximum numerical risk.
We're always trying to minimize risk. However, what we want to do is we want to get a uniform guarantee over deviations between the empirical risk and the true risk. This is the empirical risk. And what we want to make sure is that the true risk is if I pick the empirical risk minimizer here, it may very well be that the true risk minimizes it somewhere over there. That could happen. That, you know, the solutions may be even remotely close. Maybe the true risk looks like so. But at least I have a guarantee that my true risk is not going to be off by more than epsilon relative to my empirical risk. So in other words, if, my test, if I apply, use it on some cancer patients, if it heals them and kills 40%, and if I didn't use the drug, then maybe it will kill, 80% and, only 20% would survive, then all I need to make sure is that, and it may very well be different groups of patients, right? It may very well kill those that survive, the other ones may survive, so that's not really clear. But what I need to make sure is that at least I have this guarantee with a high confidence, with a high enough confidence that it's justifiable to use this drug. Okay. So in that case, actually, I have exactly one function, because that's just, do I administer the drug or not? But if, for instance, I end up testing 20 different drug regimes with different concentrations and so on, then I basically have to pay the log delta, the log 20 for it, because I now tried out 20 different solutions. And I might have just gotten lucky in one of them. Okay. Is that sort of kind of clear? Okay. Yep.
So putting like basic dimensions would be very hard to estimate.
Yes, so the VC dimension is extremely hard to compute. There are some specific cases where you can. Furthermore, the VC dimension actually misses out on a lot of things. So one case in point, and this is essentially where then more refined analysis departs from, is that it doesn't really have a notion of scale. So it's basically just for binary classification. So if you then want to analyze functions that actually have that are continuous values, and maybe this function looks smooth at the large scale, and only if you look at the function at a very, very fine scale, it looks fairly coarse, then the VC dimension would still penalize you for being very coarse on a very fine scale. It's like you take a slab of glass, it's all flat, you look at it with a microscope, and maybe it's not so flat there, and you don't want to pay the price for the slab of glass being not flat at the microscopic level. So in other words, you could have functions which are essentially very smooth and just have a small deviation. And so the first thing that people did is then they came up with what's called a fat shattering dimension, where they say, well, not only do I have to classify, but I have to classify with a margin. And so this is basically John Shaw Taylor, Peter Bartlett, Bob Williamson, and Martin Anthony. So they came up with that notion. And that was quite popular for a while. And proving bounds for that is typically even harder. What I'm going to show you now is an alternative, which is still more or less state of the art, and for which getting those bounds is easier. And I'll actually walk you through the entire proof from the concept to getting reasonably workable uniform convergence bounds. And that will be the only slide in this course that has only equations on it, no text. Promise. Okay. So here's what we're really after. So the first thing to make the Armid inequality that we had before. So that one was basically a statement of the form, well, if I have some function that may be ridiculously complicated of some data, if I switch one observation out and replace it by something else, then this function cannot change by more than Ci. And then I know that the expected value and the empirical average for this function are close, which is basically the statement here. Okay. So this is the tool that we're going to use, and proved a simpler version of that before. Remember, this was basically on Monday, the Chernoff bound. What I'm really interested in is proving a bound on this quantity here, namely the probability that the supremum over all the functions in this function class, that the empirical average, so this is basically my training error, is close to the test error, that the probability that this deviation is larger than epsilon, that this is bounded. And this is a uniform convergence statement, so it's sup over all functions in this class. And we'll see in a moment why taking the soup is actually a horrible thing, because what we'll have is what's called concentration of measure. Concentration of measure means the worst case and the typical case are actually pretty close. Or in other words, your typical case is almost as bad as the worst case. That's the half-empty interpretation of the glass. Is everybody okay with what we are trying to achieve here? Okay. Okay, question?
In practical, we don't really use like with data to get like function, like smaller function space, and then only bound on those like good function. Right?
Okay. So the question is, can we be smart and pick a smaller function class and on that? So as a matter of fact, this is effectively what you're doing when you're choosing, a regularization constant or some other model selection parameter in your algorithm. Those knobs that you have are just if. So if I pick a really small if, then, this bound is going to be really tight, but it may just happen that your performance is rather mediocre. If I pick a really large if, then this is going to be very small. But then, since I have a large function class, my bound is going to be very loose, and I just ended up trying out too many things, and there's a higher chance that I would have really gotten very unlucky. So that's exactly the point of model selection. Okay. So basically, remember quantity. This is quite a beast, right? So it depends on two things. It depends on our data and the function, of course, and it depends on the distribution. I'm now going to call this quantity here psi of x and y. Right. So some function. This is basically our really complicated function that we're going to use for McDiarmid. Okay. So now what I'm basically trying to do, and this is a very common approach to how people get those concentration of measure inequalities. So you have some random variable. You want to show that it's well behaved. What you then do is, in the first step, you show that it's typically not much worse than its expectation. And in the second step, you bound the expectation. So it's this two-step approach, and we're going to go through this exactly here as well. And this is a very, very common design pattern, if you will, in getting theorems, basically. You have some ugly quantity, prove that it doesn't deviate too much from its expectation, then compute the expectation. Okay? So the idea is basically if we change only a single observation pair, right? We only replace a single xi, yi by something else, let's say some xi prime, yi prime. In that case, well, so it's only going to change at one point. And since I only change it at one point, so therefore the soup, the most can deviate for any given function. So if that deviation is bounded by L, then basically this really horrible quantity, psi or chi, whatever you call it, is not going to be more different than L over M by just, replacing one guy.
So L is a bound on small f, right?
It's a bound for L of x, y, and f.
If you put the previous slide there,
Yeah. So yes. So McDiarmid was stated in ifs. These ifs are not these ifs. Okay. Sorry about that. These two ifs have nothing to do with each other. This guy here is our if. So what happens is, by basically just swapping one guy out, my entire badness of this deviation doesn't change by more than L over M. After all, this is the quantity I want to bound, right? And what I'm now about to show is that the typical worst deviation isn't much different from the worst way how those things can deviate. Right. So that's the first inequality. So basically, this quantity minus its expected value, being greater than epsilon, is bounded by 2e to the minus 2m epsilon squared over L squared. So this is standard McDiarmid applied to this. Okay. It's pretty good news. Okay. Now comes the horrible slide. Promised? This is the worst slide of all. Okay, because what we now need to do is we now need to compute its expected value. Okay, so on top is what we want to compute. So one thing that I can do is I can go and, okay, let's look at the second line. So the first line is clear, that's exactly what we set out with. The second line is the same thing as the first. All I've done is I've just now replaced this expectation by over x and y by a sum by the expectation over an average over m observations. Those guys don't exist, those xi primes and yi primes, they don't exist, but they're just drawn from exactly the same distribution from which I drew the x and y pairs. So by linearity of expectation, this is equal. This thing is also called the ghost sample. So the same thing, but there it's a little bit harder to understand. But basically what I'm introducing is a second fake sample. In my training data, I have another fake set of training proof. At, well, how bad is the deviation of my training error here and the training error on basically another data set of the same size. Okay. Now the next thing that I'm doing is I'm pulling this expectation out of the soup. Means I get an upper bound, and that's just the case from convexity. Simply because, well, essentially what happens is E of f of x is greater or equal than f of E of x. So to prove that in a picture, that's our convex function. Maybe these are 2 points. The expectation sits here, and that's below. Right. This is just the end. So the step from line 2 to line, so the step from line 1 to line 2 is just exploiting linearity of expectation. Okay. That's not very hard, right? Everybody has done that before. The sum over 2 averages is the average of, is basically the average of the sum. Right. Now, going from second to third line is really just using the instance inequality, and so exploiting the fact that I have, well, that I can pull the expectation out, and so the quantity will only be upper bound. Okay. But now something really cool happens, right? So we now have the expectation with regard to our true sample, and the expectation with regard to our ghost sample. So the x primes, y primes. Over the soup, over the training error for my true sample, and the training error for the ghost sample. But there's one important thing, that the ghost sample and the true sample are drawn from the same distribution. Right? They're both drawn from P of x and y. So in other words, you're taking the difference between 2 random variables which come from the same distribution. So therefore, whether I take this or whether I swap it, it's the same value, right? So I can swap it in arbitrary ways, and I still get the same quantity out of it. And this is the only non-trivial part of the proof. So therefore, I can add another random variable here. This is called a Rademacher random variable. That's why it's called Rademacher Averages. And this random variable has values 1 or minus 1. And if it's 1, it does nothing to this. And if it's minus 1, it swaps them around. But since they are drawn from the same distribution, I can just keep this. So this equality is non-trivial, right? You need to realize that they come from the same distribution, so I can swap it around. 1 and minus 1 with equal probabilities. So, but 1 and minus 1 is kind of convenient here. And since it's the same distribution, these guys, I can swap them at will. Okay. And now, I'm just applying triangle inequality. Because, well, the sup over the difference between two terms is less equal than the sup over the first plus the sup over the That's obvious, right? But then you realize that the first and the second term actually have values. They come from the same distribution. And the first term now only requires the expectation over x and y. The second one only over x prime and y prime. So I just get a factor of 2. And all I've done is the m out here. Here we have this. Okay. And this is a really awesome quantity. So the guy who came up with this, actually the two guys, is Schacher Mendelssohn and Peter Bartlett. So it's a very nice JMLR paper which explains that reasoning in a lot more detail. It's, I think, from around 2003 or so. So now let's stare at this quantity a little bit more, because this is a fairly deep and fundamental derivation that we made here. So this is the sup over an average over losses, but they're not just losses. They are with signs 1 and minus 1. So what this does is it basically almost means like, well, I'm taking a data set with random labels. You could do that, for instance. And I'm trying to see how well I can do how well I can classify on average things that have a random set of labels. So if my function class is very powerful, regardless of the labels, I can always, classify correctly, or as incorrectly as possible. So we're taking the sup here, right? Whereas if it's restricted, then I won't be able to do terribly well for random sets of labels. And this is essentially the generalization of this heuristic. So, by the way, there's also a way of how good you data set, you randomly permute, basically randomly assign the labels, you retrain, and you look at your classification error there. If you do this is essentially how much applying the overfitting, and this is essentially just puts that into math. So let's put it all together, and I'll show you afterwards for some interesting function class how you can compute this. Okay. Any questions so far? Because as promised, this is the worst slide of the entire class. Yes? Or actually, I think you've already asked a fair number of questions. Let's ask somebody else.
So do you mean that sigma i's are labels instead of something you add to make the proof easier?
So those sigma i's are actually a means of essentially looking at the expected value of, let's say you were to scramble things in arbitrary ways, how well could you do? So as a matter of fact, you could actually use this as a computational device, right? No reason why you should actually go and prove theorems for this. I mean, people have proven a lot of theorems for this. But you could just say, well, let's draw some x and y pairs, let's draw some sigmas, and then let's compute this entire object. And you do that for a lot of x and y combinations. You can get numbers out of it, and that will give you a guarantee. This is an entirely computational device then to get good theoretical bounds. And if you do it often enough, and you might have to do it, a couple of thousand times, so this could take a very long time, you will have a good, computational uniform convergence bound. But since it might actually be very, very expensive, people usually don't do it. Yes?
Do we just resample from the original data to the expectation of the function?
So the question is, do we just resample? Well, actually, the entire reasoning is a little bit more refined because there are statements which depend only on the actual sample size and statements which hold with regard to the entire distribution. Here, what I've done is I've derived a statement that depends only on the distribution of the data. And since you actually don't know what that distribution is, you may have to upper bound things further. Basically, soup overall distribution. So that's what you can read up in this paper in a lot more detail. But that's a very good question. So in practice, what you often do is you just get distribution-independent statements. But all you would need is just a statement for the specific distribution that you're working with. Pardon? No, you would actually have to draw from the true distribution. And if you don't have that, then you need to figure out a way of finding the worst case distribution.
One thing you can do, right, is if little l is Lipschitz, you can get rid of any dependence on x and y themselves, right?
Yeah. So
that would be one good way to get a distribution-independent map.
So as a matter of fact, this is what people do. Okay, so let me just write out the overall theorem that you get. And, namely, okay, so the overall theorem is that therefore the expected risk is less equal than the empirical risk plus 2 times the Rademacher average over this function class with the right sample size and so on, plus, and then here is basically the Chernoff bound, or actually McDermott that we invoked here for the loss. So this is basically the typical case. This is the worst case. This is the training error. Now, in general, function classes, which is basically I take my function class and run it through my loss function. I get something out of it. Then the Rademacher average so that's also proven in this paper. But that's a slightly less surprising result than the theorem itself. And there are a couple of straightforward things, like if I multiply my functions by 5, then the Rademacher average goes up by 5. Well, multiplies by 5. Yeah. So it has a lot of really nice properties, which mean that if I do obvious, straightforward things to my functions, then the guarantees will follow. Now, the obvious question is, that's a very nice result, but can you do anything useful with it? And what I'm going to show you now in the next 10 minutes is a derivation for kernels, how this can actually pan out. Okay, so this is not on the slides because I wasn't quite sure we'd even get to this. What I mean the expectation over x for the moment. I'm just going to compute this expectation over sigma sup here. I'm interested. Well, otherwise I just rescale it. Okay. Does somebody have an idea how we can simplify it further? Well, so if I have two vectors and I say, well, maximize the product between those two vectors. Let's say this is, one vector, the other one has unit length. Then obviously what you can do is just those two vectors align. And since that second vector has unit length, it's just using the normal quantity here. I managed to get rid of the sup. So this is 1 over m expectation over sigma. But it's still not very nice because, well, norms are kind of not so much fun. Squared norms would be easier. So what I'm going to do is I'm going to say this is less equal than now let's what's the not equal to j? 0, exactly. What happens if I equals j? Then it's 1. Perfect. Now, if we have a Gaussian RBF kernel, k of xi and xi is 1, right? Okay. So, and this is now a statement that's independent of even, you know, the xi's. So therefore, it clearly holds an expectation over all the xi's. And what we get is basically a statement that goes like empirical risk plus 2 over square root m, or actually 2 norm of the, you know, the parameter vector times, you know, Lipschitz constant divided by square root m, plus another term that goes like 1 over sample square root. Those two together will behave like 1 over square root, order 1 over square root sample size, which is exactly the rate that you want. Okay. Okay. Any questions so far? So you can do this for other function classes as well, and you'll get corresponding dual norms. So if you have a Banach space, you will get the dual norm of that Banach space showing up here. Then you can maybe play some tricks about, you know, what you know about those norms, maybe about the function spaces. And this gets rather more sophisticated very quickly, but you can still do it.
Actually, I was trying to verify that I and j are different. And generalize, I thought that the Banach from 0 to 1 actually, the Banach is either -1 or +1, right? So
Yes,
different,
correct. The Rademacher variable is 1 or -1. And the value of sigma I, sigma j is 0 if I is not equal to j and 1 otherwise. This is, by the way, an extremely useful trick if you want to compress or project things. In case you have some spurious expectation to get rid of, quite often it will not cost you anything in expectation to add those ±1 valued random variables into your analysis, and they'll just kill off all the you know, spurious correlations that you might have. So for computing this can actually be extremely useful. Good. So this is essentially all that I guess you guys would ever want to know about learning theory in this class. Next week is going to talk about some things that are maybe a little bit easier to implement. So for instance, you know, looking at validation sets, looking at cross-validation. We'll later on get to Bayesian statistics. And Bayesian statistics, in a way, has this kind of very appealing, kind of very bizarre idea that, well, you have a prior, and so therefore you know exactly what you should be seeing, which, of course, isn't entirely true, but it's kind of sort of a good working hypothesis. And yeah, that's all we're going to do. So, any questions so far? Okay.
Remind you about the homework. Homework is out. If you haven't looked at the website, homework 3 is out. It's on the website. It's due week from today. Is that right? It's supposed to be much shorter than previous homeworks, but don't wait to start it.
Yes. So the other thing is, since there will be probably only 4 homeworks, there will be a sort of 5th problem set, because we promised best n-1 out of n. And so that 5th problem set will give you a chance of boosting your homework scores if you feel the urge to do so. Okay. Can somebody please stop the camera? If you can please press the stop button. Thank you.